Imagine if, like, instead of running at full power all the time,
Yeah.
a large language model like ChatGPT could shift gears depending on the task,
Yeah.
saving energy and being faster.
Right?
That's the basic idea behind adaptive computation.
Mm-hmm.
And it's what we're diving into today with the research paper Duo-LLM, a framework for studying adaptive computation in large language models.
That's right.
So this paper is all about exploring how to make LLMs more efficient without sacrificing their abilities.
Exactly.
So the big question here is, can we make LLMs use just the right amount of computational power for each word or task, instead of the one-size-fits-all approach they use now?
Exactly. The paper's abstract even points out the inherent inefficiency in current LLMs.
Okay.
They use a fixed compute budget for every single token, regardless of whether it's a simple word like the or a complex concept like relationship.
It's like using a bulldozer to pick up a feather.
Yeah.
And the introduction section emphasizes how this fixed compute budget approach leads to wasted resources and holds back performance optimization.
Yeah, and the interesting thing is that LLMs themselves have inspired more efficient architectures like mixture of expert models or MOEs.
Okay.
The paper explains how Duo-LLM builds on this concept.
Okay, so MOEs are like having different specialists within the LLM, right?
Yes,
Each expert handles specific types of input.
precisely.
Okay.
In Duo-LLM, as shown in Figure 1, each layer has two modules. A big one for the tougher stuff and a small one for the easier stuff.
So instead of that one-size-fits-all compute budget, Duo-LLM can dynamically route tokens through different modules based on their complexity, as we see in Figure 1b.
Right.
And it can even skip certain layers entirely.
Yeah.
Oh, wow.
Now, to test the potential of this, the researchers used what they called an oracle,
Okay.
described in Stage 2, oracle-guided optimal routing.
Right.
This oracle explored every possible routing option for a sequence of tokens.
So it's like having a cheat sheet
Yes.
to find the absolute best way to route those tokens for maximum efficiency and accuracy.
Yes, and the patterns revealed by the oracle are quite interesting.
Okay.
Figure 2a shows that when you have a limited budget of big layers, the oracle tends to concentrate their use in the later layers of the model.
It seems like the later layers might be doing the heavy lifting when it comes to generating coherent and meaningful output.
Possibly, but what's even more surprising is Figure 4b.
Okay.
Sometimes using just one big layer outperforms using big layers everywhere.
Wait, so you're telling me that sometimes using LLM's compute power actually gets better results?
It surprised us too.
That's pretty counterintuitive.
Yeah.
You'd think more power always equals better results.
It seems that overloading the model with big layers can sometimes be detrimental. It's about finding that sweet spot.
This raises some important questions about the nature of the tokens themselves.
Yeah.
The paper brings up the concept of token difficulty in section 3.2.2, suggesting that some tokens are inherently harder for the LLM to process than others. Think about it. Even for a powerful AI, some words are trickier than others.
Yeah.
The researchers found that, as shown in Figure 5, predicting the word relationship is much harder than research, even when using larger models or the oracle.
Right.
So Duo-LLM isn't just about adding more compute, it's about identifying which tokens really need that extra power.
Exactly.
We want to avoid wasted effort on the already difficult ones.
Exactly. Now, of course, training a real-time router to make these decisions on the fly is a challenge.
Right.
That's where Stage 3, approximating oracle routing with learned strategies, comes in.
So how did they approach this training challenge in Duo-LLM?
They used a method similar to conventional mixture of expert models, training a router to assign tokens to the appropriate module based on their predicted complexity as detailed in Stage 3 of the paper.
But Figure 3 shows a difference between the oracle's ideal routing and what trained routers actually do.
That's right.
It seems we're not quite there yet in replicating that perfect token allocation.
That's right. Figure 7 illustrates this, showing how the router's decisions for a single sequence can deviate from the oracle's optimal path, especially towards the end. Figure 4c also emphasizes this, demonstrating that a consistently applied budget can sometimes yield better results than one that fluctuates.
It highlights the complexity of the problem. It's not just about understanding token difficulty. It's also about predicting how that difficulty will evolve throughout the generation process.
And this brings us to the training of the Duo-LLM itself, which is explained in Section 3.4. The researchers explored two methods, training from scratch and freezing a pre-trained big module while training the small modules.
Figures 8a and 8b show that training from scratch generally leads to better accuracy.
Yes.
And it's fascinating that even with only half the exposure to tokens, the big module in Duo-LLM nearly matches the performance of a traditional dense model.
That speaks to the potential efficiency gains of this adaptive approach.
Wow.
However, Table 8c shows a significant accuracy gap when using the frozen big module method, suggesting that training both modules together from scratch is crucial for optimal performance.
So while the Oracle gives us amazing insights, we still need to figure out how to train routers that can make those smart decisions in real time.
Yes, and that's where a lot of the future research will be focused. But the potential of Duo-LLM is clear. More efficient, more targeted use of compute power in LLMs.
Yeah.
This research with Duo-LLM is really just scratching the surface when it comes to adaptive computation in LLMs.
Yeah, it feels like we're on the verge of a major shift in how we think about LM architecture and computation.
The Duo-LLM framework provides a valuable tool for researchers to explore these adaptive computation strategies in more depth.
Right.
Section 4, the related work section, highlights some of the key areas being explored, like speculative decoding.
Right, where a smaller model takes a first stab at generating tokens, and then a larger model checks its work.
Yes. The paper also mentions mixture of depths, where layers are dynamically skipped based on the input's complexity.
So instead of a fixed architecture, the model can adapt its depth on the fly.
Exactly. Then there's Flextron, which converts a pre-trained model into a nested structure, allowing for even more fine-grained control over computational allocation.
It's fascinating to see how these different approaches are all converging on this idea of making LLMs more flexible and responsive to the demands of each task.
The paper also touches on research into LLM functional analysis in Section 4.
Okay.
This is about understanding what's actually happening inside these black boxes.
It's like trying to understand the inner workings of the human brain.
In a way, yes, there's a lot of work being done on analyzing neuron behavior, trying to decipher what individual neurons or groups of neurons represent.
And understanding the role of the different components, like self-attention and feed-forward networks.
Duo-LLM contributes to this by providing a framework for studying the behavior of these modules in an adaptive computation setting.
It's like giving researchers a new lens through which to examine these complex systems.
The paper's conclusion in Section 5 does a great job of summarizing the key takeaways from this research.
Okay.
The Oracle results are particularly striking.
They really demonstrate that optimal routing can lead to significant performance gains, even with limited compute resources.
And that the traditional notion of token difficulty might need to be refined, considering not just the loss associated with a token, but also its potential for improvement with additional computation.
That subtle distinction could be key to unlocking even more efficient and targeted use of computational power.
The paper also acknowledges the limitations of the current framework.
The reliance on an oracle for optimal routing isn't feasible in real-world applications.
Right.
And training effective routers remains a major challenge.
However, Duo-LLM serves as a valuable starting point, paving the way for future research in adaptive computation.
In the appendix section A, the researchers provide some bonus insights from their work with the OPT 1.3b model.
They trained a router on top of this model and observed some interesting patterns. For example, early layers tend to favor the small module, while later layers get more access to the big module.
So it's like a relay race, with different modules taking the lead at different stages of the process.
And there's a similar pattern with tokens, where early tokens often utilize the big modules, but later tokens benefiting from the context built up require less compute.
It suggests that the demand for computational resources isn't evenly distributed throughout the model or the generation process.
These additional findings provide further evidence of the potential for adaptive computation to optimize LLM performance.
They also highlight an interesting parallel between layers and tokens when skipping is an option.
The researchers observed that early layers and tokens tend to skip less, while later layers and tokens skip more.
It's as if the model front-loads the computational effort, building a solid foundation, before becoming more selective about where to allocate resources.
Precisely. And this observation further reinforces the idea that the computational demands of language processing aren't static, but rather ebb and flow throughout the generation process.
It seems like this deep dive into Duo-LLM has really illuminated the intricate dance between computation and language.
Yeah.
It's certainly revealed not just the inefficiencies of current LLMs, but also a potential path toward more agile and adaptable models in the future.
Right.
Models that are more aligned with the nuances of human communication.
Yeah.
This has been a fascinating deep dive, and I'm eager to see what breakthroughs emerge in this exciting field of adaptive computation.
Definitely.
Until next time,
Yeah.
keep exploring,
Uh-huh.
keep questioning,
Yep.
and keep diving deep.